Now to the Nobel Prize for Physics. John Clarke, Michel Devoret and John Martinis have won the prestigious award for their work in quantum mechanics. Organisers said discoveries by the US-based academics demonstrated how the bizarre properties of the quantum world can be made concrete on a human scale. Well, let's try and discuss this and find out more about it with the theoretical physicist and YouTuber Dr. Sabine Hossenfelder, who joins us now from Heidelberg in Germany. Really good to have you with us. And I want to begin by reading for our audience what the Nobel Committee said this award was for. Let me find it. I have it in front of me. Here we go. The discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. Now, that sounds pretty dense. I guess even if you're, someone with a pretty scientific mind, that might sound pretty dense. Explain for us exactly what they have won this prize for.
Broadly speaking, I'd say they won the prize for developing the basis for modern quantum technologies. So there was a Nobel Prize for the quantum tunneling effect already in the 1970s, I think in 1973. But this was like on the microscopic teeny tiny scale for individual particles. And there's only so much you can do with individual particles. So this is the basic for electron tunneling microscopes that you might have heard of. So what these people did was they figured out how to do quantum tunneling for currents in a wire. So this is what they mean by macroscopic. So it's maybe not your everyday notion of macroscopic. So when they say human scale, it's not like actually the size of a human, but it's a current. And this raised it to a level where it could be used in microchips. So it created this synergy between the foundational research in quantum mechanics and semiconductor industry. And so this is basically what today's quantum computers are built on. It all goes back to this research which they did in the 1980s.
So tell us more then about what this particular research and this discovery, how that might impact on our everyday lives.
So I guess most people have kind of heard of quantum computers. So roughly speaking, a quantum computer can do logical operations that a standard computer can't do. And because it can do other quantum operations, it can do certain calculations much, much faster. So we do have quantum computers by now. So in the 1980s, this was purely theoretical. We now actually do have quantum computers, and they're built on this idea that they worked out, most of them are built on this idea that they worked out in the 1980s. And so there's a huge potential in being able to do some calculations dramatically faster. And the most widely known example is that it could be used to break certain codes. So it's not an application that you and I would be using, I assume. But there are other applications, like there are optimization issues in logistics or in finance. So banks are very, very interested in quantum computers.
OK, just one final thought from you, if I may, and we have less than a minute. Is it unusual to get an award like this for work that was done literally decades before? Has it taken that long, really, for the significance of this research to be fully recognised?
Well, it depends on who you think has recognized it. I think people in the community have long recognized that because they built all this work onto it. But I think what really happened here is that most physicists expected that there'd be a Nobel Prize for quantum computing at some point. And I think what the Nobel Prize Committee was thinking is that we'll go back to the experimental work that it actually builds on, rather than looking at what was done later. For example, they could have given out a Nobel Prize to more recent proofs that quantum computers actually work. But I think they made a good decision going back to what it all was built upon.
Sounds like Back to the Future to me. Sabine Hossenfelder, thank you very much. You're watching BBC News.